Hello everyone, this is lecture 4, System of Difference Equations. So in the last few lectures, we look at difference equations individually. Now we're going to combine difference equations into a system, and what we're going to do is we're going to view the system of some system of difference equations from some example, and gonna build the numerical solutions to get an indications of long-term behavior of the system, as well as we're gonna find the equilibrium values and explore the starting values or the initial value or initial conditions. All right, so first I'm gonna write down the definitions of equilibrium value, or it's another name for that is called fixed point. So a number C is an equilibrium value or fixed point of a dynamical system, a sub n plus 1 equal to f of a sub n, if you have a sub k equal to that constant c for all value of k from 1 to 3 and goes on forever, when a is 0 is equal to c. That is a sub k equal to c is a constant solutions. To the dynamical system. Okay. You start at one value. You're going to put that into the dynamical system, calculate a sub 1, a sub 2, so on and so forth, up to a sub n plus 1. And if you obtain the same value c, then you're going to get the value a sub n plus 1 or equal to a sub n. It's going to be the equilibrium value or the fixed point. Okay. And not only that, you can start at the same value c. You can start at different values, and if it's going to approach the same value c, then it doesn't matter. On the initial conditions, the system always reach the equilibrium value. Okay, so I have some example in terms of graphs here. You have the system. This is the linear dynamical system that we talked about in lecture 3, where you have the first part to be exponential, related to exponential functions, and the second part is the constant functions. The equilibrium, so right, I'm not going to show the detail, but the equilibrium is the point at which you have x equal to b over 1 minus a. And this is the value c right here. So c equal to b over 1 minus a. So how could so this is an equilibrium that we solve, that we can solve. And we can classify this equilibrium as stable equilibrium. Because no matter where you start on the initial values, the sequence always going to approach the equilibrium, right? So if you start on the left of this equilibrium point or the fixed point here, then as you can see, the functions will approach, or the sequence approach this equilibrium point. If you start on the right of that, is also get degrees and get approaching to the equilibrium. Now, there's another state for equilibrium is called the non-stable equilibrium. And again, in this case, you have this equilibrium point, and depends on where you start for the initial value, it can diverge to the positive infinity, or it can diverge to negative infinity. And in this case, we call that unstable equilibrium. Right, so there are multiple states to equilibrium point or equilibrium value, but we just going to focus on this two main state, either stable or unstable. Okay, there's another graph here that we can look at in terms of stable or unstable equilibrium point. Is that I have 2 points right here. These are two equilibrium points. Right. So this is equilibrium point. This is also equilibrium value, right? Or equilibrium point. Okay. If the initial conditions start on the left of this point, I call this P1, and I call this P2, right? If the initial conditions start on the left of P1, it's approach P1 after a certain time period. If it gets started on the right-hand side of P1, it's also pointing back to P1. So because of this, we call this is the stable in equilibrium. So this is a stable, right? Because all the solutions point back to the equilibrium point. However, when we talk about P2, the solutions start on the right of P2 will get moved away from P2, right? Diverges away from P2. And if the initial conditions start on the left of P2, it moves away and point back to P1. So this is called the unstable equilibrium. So these are the few examples that you may want to know about equilibrium points or stable and unstable equilibrium points. Okay, now we're gonna move to some examples. What we're going to do is we're going to build a model of a system of different equations, and we're gonna test the model, find the equilibrium point, and we're going to see if the equilibrium point is stable or unstable. Okay, so in the first example, you have a car rental company. Right? So the historical records reveal that 60% of the cars rented in Orlando are returned to Tampa, whereas 40% end up in Tampa. Right? Of the cars rented from Tampa office, 70% are returned to Tampa, whereas just 30% end up in Orlando. Okay, so this is very much the real life situation because sometimes we want to go to a road trip and we rent a car, let's say in Orlando, and we go to Tampa for vacations and we don't want to drive back to Orlando, we can just leave the car in Tampa, right? So, or there's another situation where you can just commute back and forth between Orlando and Tampa, and then at the end you return the car in Orlando, so on and so forth. So this is very much the real life situations that we can experience. So again, we're gonna build a system of different equations from this particular example. A few assumptions that we need to make for this model is that a traveler will rent a car in one city and drop the car off in the second city, right? There will be there will no third city in the problem. Travelers may begin their itinerary in either city. You can start in Orlando or in Tampa, it doesn't matter. The initial value or the total number of cars is going to be $7,000. 7,000 cars for this particular company. And they have 3,000 car in Orlando and 4,000 car in Tampa. Okay. Okay, so now let's build up the model. So I have two cities, right? So one is in Orlando and one is in Tampa. So on Orlando, this is Tampa. Okay, and follow along the information given to us. You have 60% of the cars rented in Orlando are returned to Tampa. So I make a mistake here, a typo here. So this is not Tampa, but Orlando. So there is a 60% that the cars rented in Orlando are returned back to Orlando, and 40% chains end up in Tampa. All right, so let me put this information into the schematic. So this is Orlando, this is Tampa. So there are 60% that the car rented in Orlando get returned in Orlando, and 40% chains that the car rented in Orlando get returned in Tampa. So this is 40%. And in the Tampa office, there's 70% that the car rented in Tampa get returned in Tampa as well. And there is 30% chance that the car rented in Tampa get returned in Orlando. Okay, so now we're gonna build of the system of difference equations. So I'm gonna put some naming conventions here. So for O sub n, this is the number of cars in Orlando at the end of day n. And T sub n is the number of car in Tampa at the end of day n as well. And n is the number of days. Okay, now we're gonna build a system of difference equations, right? So you have the number of cars in Orlando and in Tampa at the end of day n. What happened to the day n plus 1? So what we're gonna do is we're gonna set O sub n plus 1. Remember that there are 60% that the car rented in Orlando returned back in Orlando. So you have 0.6 times O sub n. And there is a 30% chance that the car rented in Tampa get returned back to Orlando. So we get plus 0.3 T sub n. That's for the equations of the number of cars in Orlando at the end of day n plus 1. Okay. Now for the T sub n plus 1, what you do is you get the cars rented in Orlando return back to Tampa, and there is a 40% chance that could happen. So 0.4 times O sub n plus there are 70% chance that the car gets rented in Tampa, get returned in Tampa. So there's 0.7 times T sub n. So that's the system of difference equations that you need to build for this particular model. And what we're going to do next is going to find the solutions or equilibrium values of the system. Right, so next we are going to determine the equilibrium values of the system. So that means what you're looking for is how many cars Orlando office get and the Tampa office get as we run this model for a long period of time. All right, so a quick definitions again for equilibrium values, that the equilibrium values for the system are those values of O sub n and T sub n for which no changes in the system take place. Okay. So again, after you run this model for a long period of time, you reach an equilibrium values that is m equal to m, sorry, O equal to O sub n plus 1 equal to O sub n. For O is the equilibrium values of the number of cards in Orlando office, and T is equal to T sub n plus 1 equal to T sub n, and T is the equilibrium values of the number of cards in Tampa office. And this gives you equilibrium value. Okay. Now to find the relationship between the number of cars in Orlando and the number of cars in Tampa, what you do is you substitute this equilibrium values into the system that we built earlier and find out the relationship between O and T. So substitute O and T into the system of difference equations. We get that. So now O sub n plus 1 becomes O sub n also becomes O, T sub n plus 1 becomes T, and T sub n also become T. Therefore, you get the new system of the form O equal to 0.6 times O plus 0.3 times T, T equal to 0.4 O plus 0.7 T. Now, if you solve for, if you combine like terms and for this two system, what do you see? You see that you have negative 0.4 O plus 0.3 T equal to 0, and positive 0.4 O plus 0, sorry, minus 0.3 T equal to 0. So that is the system is satisfied whenever you have O equal to 3/4T. Okay, so if you do a quick calculations here, for this two system, it will give the same value of O equal to 3/4T. Okay. Now at the beginning, we have the initial value that we that's given to us. That is the company owns 7,000 cars in total. And we're gonna start with 3,000 cars in Orlando and 4,000 cars in Tampa and see what's going to happen. So for example, the company has 7,000 cars in total. 3,000 in Orlando and 4,000 in Tampa. Right. Then the model predict that if you calculate M1, right, you get 0.6 times 3,000 plus 0.3 times 4,000. M2 is, sorry, T1 is equal to 0.4 3,000 plus 0.7 4,000. Right. If you do the calculation for these two values, you will get that there's 3,000 cars in for M1 and 4,000, sorry, O1. and 4,000 cars in T1. Okay. This implies that the system remains at the equilibrium point. So 4,000 for the number of cars in Orlando and 4,000 cars for the number of cars in Tampa. Okay. Now we're going to explore different values of the initial conditions, right? So I assume that in this case, you start with 7,000 cars in Orlando and no cars in Tampa. And after a long period of time, so after a few weeks, right? So n is the number of days. After a few days, after a week, you can see that the system go back to the equilibrium point, which is 3,000 for Orlando and 4,000 for Tampa. Now you explore all the initial conditions. So Orlando, there are 5,000 cars in Orlando and 2,000 cars in Tampa. Again, they reach the equilibrium point after certain days. Similarly, in the case of 2,000 cars in Orlando and 5,000 cars in Tampa, they also reach the equilibrium. So another extreme that you can have is there's 0 car in Orlando and 7,000 car in Tampa. And again, after a while, the system reached the equilibrium point that they have to have 3,000 car in Orlando and 4,000 car in Tampa. Okay. And we can actually find this equilibrium point is from this particular relationship between O and T, right? So O is always equal to 3/4T for this system of equilibrium points to work, because remember the total number of cars will be 7,000 cars, right? So that is the relationship that we can obtain, 3,000 and 4,000. Okay. Okay, so now after testing a few initial conditions, we can draw conclusions on the sensitivity of the initial conditions in the long-term behavior. So in each of the cases, the system remains at the equilibrium point for 3,000, 4,000, even in the absence of any cars at one of the two sides. So this suggests that the equilibrium value is stable and insensitive to the starting value or the initial conditions or the initial data. Okay, so hopefully it gives you some idea how to build this system of different equations from a given data, calculate the equilibriums, and show different outcome when you choose different initial values, and then draw conclusions at the end that will the equilibrium points a stable equilibrium point or unstable, and then will the system be sensitive to the starting values or not. Now let's move on to a similar problem but instead of two different things that you have to do with, now you have three different objects that you're going to work with in example 2. So in example 2, travelers' tendency at the regional airport. Right, so consider a regional airport that is supported by 3 major airlines: American Airlines, United Airlines, and Delta Airlines. We surveyed weekly local business travelers and find that 75% of those who travel on Delta travel again on Delta. Right? And 5% switch to United, and 20% switch to fly American Airlines. Of those who travel on United, 70% travel again on United, 20% switch to Delta Airlines, and 20% switch to American Air. And then of those who travel on American Airlines, only 40% remained with American Airlines, 40% switched to Delta Airlines, and 20% switched to United Airlines. All right, and before we put the information in the schematic below, I'm gonna make a couple of assumptions that this tendency continue week to week, right? So there's no change in the tendency of move from one airline to another, different from what already given here in the example. And there's no additional local business travelers enter or leave the system, right? So it's a closed system. That means no new travelers and no travelers leave the system, okay? Even though the informations here given to us are somewhat realistic, the assumptions are not that realistic because we only have additional business traveler and people will only always leave the system, okay? But that's for another more complicated model. Now let's put this information into our schematic here. So there are 3 airlines: Delta Airlines, United Airlines, and American Airlines. Now I'm gonna start with, this is Delta Airlines, this is United Airlines, and this is American Airlines. Okay. So for Delta Airlines, say that 75% of those who travel on Delta travel again on Delta Airlines. So this is 75%. 5% switch to fly United. So this is 5% that use Delta before now switch to United. And there is 20% switch to fly American Air. So this is the arrow. Right, so this is 20%. Now we move on to United Hub, right? United Airline Hub. So of those who travel on United, 60% travel again on United Airlines. So 60%. But 20% switch to Delta Airlines. So this is 20%. And 20% switch to American Airlines. So 20%. Okay. Now for the last case for the United Airlines, American Airlines. Of those who travel on American Airlines, only 40% remain with American Air. So this only 40%. 40% switch to Delta Airlines. So this is 40%. And only 20% switch to United Air. All right, so this schematic captured the information given to us in example 2. Now, using this example, we're gonna build a system of difference equations and try to understand the equilibrium point of the system. Okay. So some naming conventions now. So we let D sub n be the number of Delta Airlines traveler in week n. And then U sub n is the number of United Airlines traveler in week n. And American Air, so A sub n is the number. So do this. of American Airlines travelers in week N. Right, so N for N is the number of week. Okay, now you go, because you have three different objects that you will have to deal with, therefore there will be three equations in the system. So for d sub n plus 1, what you're going to get is, so 75% of people who use delta will continue using delta. So 0.75 d sub n. There is 20% who use United will switch to delta. So 0.2 times u sub n. And there is 40% of people who used American Airlines before will switch to Delta Airlines. 0.4 American Air. Right. So that's the first equation for the Delta Airline. Now move on to United Airlines. What I want to do is I want to light up the variable d sub n, u sub n, and a sub n. Right? So therefore, I'm gonna do what I'm going to do is I'm going to do with delta move to United first. So there's only 5% chance that people who use delta will switch to United. And there is 60% people who use United before will continue using United. And 20% of people who have who use American Air before will switch to United Air. In the last equations, you have a sub n plus 1 is going to be 0.2 d sub n plus 0.2 u sub n and plus 0.4 a sub n. Right. And if you notice for this example and the last example is that the percentage of delta will add up to 100%. The percentage of United Air will also add up to 100%. And the percentage of American Air add up to 100% as well. Okay. Now the next thing we need to do is to find the equilibrium points. Okay. So you say that let D, U, and A be the equilibrium values of delta United and American Airlines traveler, right? Respectively. That is what you're going to have is d sub n plus 1 equal to d sub n equal to this equilibrium value. Right? So after you let the system run for a long time, it will reach a certain equilibrium point. U sub n plus 1 equal to u sub n equal to u, and a sub n plus 1 equal to a sub n equal to a. So let me move these things around. So I have more room to write. All right. So now you substitute this into the system that we built up here. Okay. And so substitute D, U, and A into the system. We get that D equal to 0.75 D plus 0.2 U plus 0.4 A. The next equation is u equal to 0.05 d plus 0.6 u plus 0.2 a. And then a is equal to 0.2 d plus 0.2 u and plus 0.4 a. And this system yields the following or equivalent system, that negative 0.5 d plus 0.2 u plus 0.4 a equal to 0. Right, so basically combine like terms. Right. And then the next equation is 0.05 d minus 0.4 u plus 0.2 a equal to 0. And 0.2 d plus 0.2 u minus 0.6 a equal to 0. And from here, you can obtain the equilibrium point. And of course, there's many techniques to obtain the solutions of this particular system. You can use eliminations method, you can use substitutions. If you know linear algebra, it will also help you to solve the solutions. And it will find out, it turned out that there's infinitely many solutions for this particular system, okay? So you don't have to worry how to actually solve for this system. What you need to know for this lecture is can you put in the information given to you in the schematic and then come up with the system? Can you actually analyze or set up the equilibrium value so that you can put it back into the system and come up with this equivalent system? Okay, and then that's it. You for further information, I will let you know how to actually obtain that in the homework or in the test. But for this lecture, right, because there's so many techniques that you may not have known that before, then it will take a lot of time to explain how to obtain the solutions, right? And which is not the focus of the lecture. Okay, but we just have to know for this system that there's infinitely many solutions for the system. So it turned out that there are, what the system has infinitely many solutions. Okay, and because of that, you can there are so many solutions that you can play around with to see the to have different values of the number of travelers for Delta Airlines, United Airlines, and American Airlines. So which is okay. Now we're gonna test the stability of the equilibrium point, right? So there are 4 different cases, and the cases will give you the informations of the number of travelers starting with at the beginning, right? For Delta Airlines, for United Airlines, or for American Airlines. Okay. So there are 4 cases. All right, so we're gonna make a few assumptions here that initially you have about 4,000 travelers in total, right? And we say that there's going to be 2,222 travelers using Delta Airlines, sorry. There are 778 travelers using the United, and there's only there are 1,000 travelers using American Air. And we're gonna start with the first case, where case 1 is the equilibrium values. All right, so here's the Python code that I want to share with you. Let me walk you through the Python code here. So let me split into two different screens. One is for the code and the other one is for the lecture notes. So now the system that we got is this particular system. Right? So we say that you have a different coefficients, right? So the coefficients in the first equation, the coefficient is 0.75, 0.2, 0.4. In the second equation, you have the coefficients to be 0.05, 0.6, 0.2. And in the third equations, the coefficients are 0.2, 0.2, and 0.4. So I'm input the informations of the coefficients in here, right? In the first equation, you get 0.75, 0.2, 0.4, right? So 0.75, 0.2, 0.4. And in the second equation, the coefficients are 0.05, 0.6, 0.2. So it's corresponding to the coefficient in this second equation. And for the third equation, you get 0.2, 0.2, and 0.4. Those are the coefficients corresponding to 0.2, 0.2, and 0.4 in this equation. Okay. Now we're going to have a different initial values. And as we mentioned earlier, we're going to start with the first case where you have 2,222 travelers using Delta, 778 travelers using United, and 1,000 travelers using American Airlines. And these are the initial values that I'm going to use. Okay. So this code x sub underscore old, y underscore old, and z underscore old. It's just a name that I use to say that, okay, these are my initial values, and I'm going to use that in the code. Okay, so x equal to open and close brackets. All of this is just the setup so that every time I calculate a number in the sequence, I'm going to stack those numbers into a vector, right? So that's what I'm going to do. So I'm going to run this through a loop, right, to calculate using the previous value. I'm going to calculate the next value, right, using this formula. So there are three formulas that I need to input into the code, right? So again, n is the number of week. So I'm gonna, let's say I'm gonna run about 20 weeks. I'm gonna stack all the week into a vector, and I call that vector n. This n dot append, that means that I'm gonna stack all the values of I in the vector n. In this line of code, I'm gonna stack all the x old into the vector x, so on and so forth. I'm going to use the previous value, which is x old, y old, and z old in these equations to calculate for the new values. So this is first equations corresponding to d sub n plus 1. Right. And this equation corresponding to u sub n plus 1. And the last equation here corresponding to a sub n plus 1. Right. Now, when you know the next value, you want to use this new value to calculate for the next value, right? So let's assume that you use a sub 0, b sub 0, or d0, u0, and a0 to calculate for d1, u1, and a1. Now to calculate d2, u2, and a2, what you do is I'm going to replace x old by x new, y old by y new, and z old by z new, so on and so forth. That help me to calculate for the next value using the value I just obtained. Okay. All right, now I'm gonna run the code and see what we're going to get so far. So again, this is right? So you hit Shift Enter, and this is what you see, right? So you're gonna start with this 3 values, and you can say it remains equilibrium throughout the calculations. Okay, so this line of code just to increase the size of the text in the graph or in the plot. So you plot the info of Delta Airlines. The second one is that we plot the info of United. And the last graph is to plot the info or the data of American Airlines. Right. So this line of code is just to help me make adjustment on the axis, right? So how big I want to see the vertical line, or how big I want to see the in the horizontal line. Okay, so this is X label, right? So the label for the horizontal axis, so that the horizontal axis is to the number of weeks, and this is the Y label. This is for the number of travelers in the vertical line. Okay, and legends means that you want to notify or annotate the plot, right? So there are 3 different plots. You start the first plot with delta, so you have to do legend delta. The second plot is for United, and the third plot is for American Airlines. Okay, so those are the initial values of 1,222, 778, and 1,000. Now we move on to the second case. Now the second case is, so now the second case is you have originally have 2,720 travelers using Delta Airlines, 380 travelers using United Airlines, and 900 people using American Airlines. So what we're going to do is we modify the initial value right here to be, so X underscore old is 2720. And for wide old, we have 380. And for American Air, we have 900 people. And we're going to run the same code again. The only change that we made is the initial values of travelers using Delta Airlines, travelers using United, and travelers using American Airlines. All right, so I'm going to hit Shift Enter. And this is what I'm going to see, right? So with different values, with different initial values, we run the code, and it turned out that no matter where you start in the second case, the values will go back to the equilibrium point, which is D equal to 2222, U is equal to 778, and A is equal to 1000. Okay. So this is 1000. Let me make a corrections here. So this is 1000. All right, so I'm gonna modify the code again so that it's reflects the new case. So in case 3, you have 1,000 traveler using Delta Airlines, 1,000 traveler using United Airlines, and 2,000 travelers using American Airlines. So I'm gonna modify the code here. So 1,000. This is also 1,000. And this is 2,000. And you're going to hit Shift Enter and run the code one more time. And so let's say for the dot connected line in black, gonna start at 1,000, and eventually it will go to the equilibrium point of 2222, and corresponding to the, let's make some mistake here. So this is American Airlines. So the American Airlines, you have 2,000 people traveling using American Airlines, and eventually it will come down to the equilibrium values of 1,000 people. And for United Airlines, we start with 1,000 people, and eventually the model shows that the people will tend to reach to the equilibrium values of 778 people. Okay, now we have the last case, which is an extreme case. All right, so you have no traveler using Delta at the beginning, no traveler using United Airlines at the beginning, and all of the initial travelers using American Airlines. So 4,000 of them will use American Airlines at the beginning. So we're going to modify the code as such. So this is 4,000. You run the code one more time. And you can see that based on our model, everything will eventually reach the equilibrium values of traveler using Delta. There will be 2222 or 2,222. The number of travelers using United eventually going to be 778. And the number of people using American Airlines eventually going to be 1,000 people, even though you start the problem with nobody at 0 for Delta Airlines, 0 for United Airlines, and 4,000 people using American Airlines, which is a very fun way to look at the problem. Because we have 4 different cases, and all of them eventually reach the equilibrium point. Okay, so from these 4 cases, you can draw quick conclusions that the model is not sensitive to the initial value at all, right? Because no matter where you start, eventually the model will show that the number of travelers will reach the equilibrium points. Okay, so that's the conclusions that we can draw, that the model is not sensitive to the initial conditions or the initial values. And also the second conclusions that you can draw is that the equilibrium point is a stable point, right? So the equilibrium point is stable. Okay, so that's 2 very important conclusions from this particular model. Okay. So again, I hope you get some idea of how to set up the system, how to determine the equilibrium point, and using different initial conditions to test if the equilibrium point is stable or unstable, if the model is sensitive to the initial values or not. Okay, so we've seen the last 2 examples. The initial conditions or the model is not sensitive to the initial values. So in the next model, is called competitive model. You will see that the model will be very sensitive to the initial value, and you will see in a few minutes. All right, so in this model, competitive hunter model, right? There are 2 populations that we're going to consider. The first one is the spotted owl, and the second population is hawks, right? So we're going to also make some assumptions that spotted owls and hawks compete for survival, okay? And no other species present the same habitat. So again, even though it's realistic, it's not really that realistic, because of course, in the environment, in certain environment, there will be multiple species in the population in the area of habitat. But for now, we just assume that there are just 2 populations, spotted owls and hawks, and they compete for survival. Also, the third assumption is unconstrained growth, in which the change in the populations during an interval time is proportional to the population size at the beginning of the interval. Okay. And the question is that will the model remain stable as initial value change? So that's always the case for always the considerations that we need to look at. All right. So now we look at the this model and see what happened. So we first determine that O sub n, which is so represents the size of the spotted owl populations at the end of day n. In H sub n represents the size of the hawks populations at the end of day n as well. All right. So the assumptions we have is unconstrained growth, which is exponential growth. So there's no carrying capacity whatsoever. Right? With the carrying capacity, you have logistic growth, but for exponential growth, it will grow up to infinity. Right? So in the third assumptions, unconstrained growth in which the change in the populations during the time interval is proportional to the population size at the beginning of the interval. So the change, right, so delta O n is proportional, so K1, right, so K1 is the constant of proportionality times O sub n, right. So this is the change in the owl populations. And we're going to do the same for the hawk populations. So delta Hn equal to K2 times Hn. All right, so this is the change in the hawk populations. All right. Now again, you have K1 and K2 are positive, constant of proportionality. Then what we're gonna do next is to incorporate the presence of the second species, right? Not only we have the owl population, but we also have the hawk populations, and they share the same habitat. They compete for survival. Okay, so we have to include that in our system. Okay, so at this for now, we have a system of two equations here. One is just for the change in the owl populations, and one is for the change in the hawk populations. So we want to include the effect of the presence of the second species is to diminish the growth rate of the other species. So if the hawk is in the population in the same habitat, eventually some owl population will die down when they interact or compete with one another. Similarly, if you have the owl population in the habitat, then there's going to be a number of hawk will die down in competing for survival in the same habitat. So therefore, the change in the owl populations can be modified as follows. Right, you have the increase in the populations. That makes sense. Now, if you introduce the second species into the model, then right, so the owl will die down when interacting with the hawk populations. So because it's die-out, so you do subtractions of K3 times O sub n times Hn. So the interaction between out and Hawk populations will eventually reduce number of out in the system, in the populations, as the rate of K3. Right? And for the change in the Hawk populations, you have K2 times Hn minus K4 times On times Hn. Right? So again, when you have the interaction between Hawk and out, then the number of Hawk will get reduced at the rate of K4. Okay. So I want to know that K3 is the reduced rate of our populations in the presence of Hawk. And K4 is the reduced rate of, be careful here, so reduce rate of Hawk populations in the presence of owls. Okay, so that's the system, right? So and we're going to rewrite this system in terms of O sub n plus 1 minus O sub n on the left-hand side of the equations. And delta Hn will be changed to H sub n plus 1 minus H sub n. So this is what we're going to get. So O sub n plus 1 minus O sub n equal to K1 O sub n minus K3 O sub n times H sub n. And delta Hn is Hn plus 1 minus Hn equal to K2 times Hn minus K4 times On times Hn. Okay. So, and we can continue with this system, manipulate the system so that the left-hand side only contain the term O sub n plus 1 and H sub n plus 1. And so we get O sub n plus 1 is equal to 1 plus K1 times O sub n minus K3 times O sub n times H sub n. And for the second equations, you have H sub n plus 1 equal to 1 plus K2 times H sub n minus K4 times O sub n times H sub n. Okay, and from here you can find the equilibrium values and you can later determine if the equilibrium values or equilibrium points are stable or not stable. Okay. All right, so we let O equal to O sub n plus 1 equal to O be the equilibrium value of the L populations. And you have H equal to H sub n plus 1 equal to H sub n be the equilibrium value of the Hawk populations. Okay, and we're going to substitute this into the system that we derive up here with the additional information that we're going to choose a specific value of rate. Right, so we're going to specify K1, K2, K3, and K4. So in addition, we set K1 equal to be 0.2, K2 equal to 0.3, K3 equal to 0.001 and K4 is equal to 0.002. So where all of this number coming from is actually you can choose any values of this constants, right? But there's another way to do that, but it's not our concern. It's just that this is a work example, and we can set the value of K1, K2, K3, and K4 to our advantage. Okay, so you don't have to worry about where's all of this coming from. It's just that we want to see the setup, and we want to know if the setup works or not. Okay, so if you are asked the questions in the test or in homework, this value will be given to you. Okay, now you substitute these values into the system. Then we get that. So O is equal to 1.20 minus 0.001 OH. And then the second equation is H equal to 1.3 times H minus 0.002 O times H. Okay. And then you combine like terms and you get that 0.20 minus 0.001 OH equal to 0. And second equations give you 0.30, 0.3H minus 0.002 OH equal to 0. Okay. Now, how could you find the equilibrium value? So this is the system of two equations with two unknowns. However, this is the non-linear system, right? Because you have the multiplications of two variables here. So this is a non-linear system. What you actually notice is that in the first equations, O is the common factor. And in the second equation, you have H is the common factor. So based on that, we're going to do some factor here. So in the first equation, you take O as the common factor, and you're left with 0.2 minus 0.001 H. Right, so I want to correct here, it's just 0.001. So 0.001. And this equal to 0. And in the second equation, you have H is the common factor. Then you're left with 0.3 minus 0.002 O equal to 0. Right. So in the first equation, you obtain two values. So either O, our populations, is equal to 0, right? That the owl populations equal to 0, or the hawk populations is equal to 0.2 divided by 0.001, or for short is 200 hawks. And then in the second equations, you have H going to be equal to 0, or O is equal to 0.3 divided by 0.002, or 150. Okay, so there are actually, in this particular problem, you have two equilibrium values. So there are two equilibriums values, or let me say points. Right. So the first point, you're going to make the combinations, right? You cannot combine these two values because they in the same equations. What you can do is mix and match, right? So this O matched with this H, and this O matched with this H. So that's why there are only two equilibrium points. The first one, OH, is equal to 0, 0. So this fixed point or this equilibrium point is at the origins. And the second point is, right, so OH equal to 150, 200, right? So there are two equilibrium points, or two fixed points for that matter. Now, if you start the populations at the total number of animals in the habitat, right, is 350, and you start with 150 owls and 200 hawks, then this system remain in the straight line, right, because this is equilibrium point. So there's no change at all throughout the interactions in the habitat, right? The number of hawks remain the same at 200 200 hawks, and the number of populations of owls is going to be 150. However, we want to see will the species or these two equilibrium points will be stable or unstable. Right, so we're going to test the system using different initial values. So what I'm going to do is just slightly change the number of owls and the number of hawks in the populations. So in the first case, you have 151 owls and 199 hawks. So to change the difference between the number of populations in the hawk, in the owl population is by 1. The change in the number of hawk in the population is just 1 as well, right? So you increase by 1 owl in the system and reduce 1 hawk in the system to see if the system is stable or not. Right. In the second case, you reduce the number of owls by 1 and increase the number of hawks by 1 as well. And also in case 3, you reduce the number of owls by 10. You choose the number of owls by 10, and you choose the number of hawks by 10 as well, and see what's going to happen. So let me go to the code and show you the calculations and see what we got. All right, so here's the setup on my screen. Again, is on one side is the lecture note, and this side is the code. Again, what I want to do is I want to see if the model is sensitive to initial value or not, or if the equilibrium point stable or unstable. Okay, so here's the code. So it's very similar to the code that we did in the last example. The modifications of the codes is that now you have 4 different rates. Raised this rate K1 corresponding to 1 plus K1, right? So it's a little bit different there. K2 is this value, right? K3 is 1 plus K2 here. Right, so this K1, K1, K2, K3, and K4 are different from what we have here. Okay, so to show you that, so what I mainly do is I'm going to use this 1.2 K1, 0.001 K2, 1.3 K3, and 0.002 K4. Okay. Now the initial value is 150 and 200, and if you notice, this is one of the 2 equilibrium points. Okay, so we want to see that can we reproduce this particular graphs at all. All right, so again, this is the setup where I'm going to store all the X value, right? So there are 2 species, so the X value will be for the owl populations, and the Y values for the hawk populations. So let me say that. So X is owl populations, and Y is for hawks populations. Okay. And we're gonna store all the values of the number of days that we want to run these simulations. Right, so n is equal to 0, 1, 2, 3. So I'm gonna do that I'm going to store up to 30 days. Okay, so I'll run this in a loop. So this is the for loop. Right. Again, this command append means that, okay, you're going to start the loop at I equal to 0. I store that in the vector n and let it run through. So I'm going to store XO or the else population in the X vector. I'm going to store the Hawk populations in the Y vector. And I'm going to find, so that is the initial value. I'm going to use the initial value with the rate I post here to obtain the new value in, or the next value in the sequence. Right? So that's mean I'm going to do the setup. I'm going to use this setup right here, right, to calculate the next value. So x new equal to k1 times xo minus k2 times xo times yo. And similarly for the second equation. Now you have the new value. You want to use that new value to calculate the next value. What you do is you set xo to be x new so that you can run back to the loop again, right? And you do this 30 times, running from 0 to 30. So again, this code means that I want to increase the size of the font, right? This line of code, I want to plot the out populations. And this code, this line of code, I want to plot the Hawks populations. Okay. So this is the label for the x-axis. This is the label for the y-axis. This is the annotation for the graph. Because I plot the OWL population first, so I use OWL as the first entry in the legend. And I plot the Hawks populations second. So this is the second entry in the legend. Now I'm gonna start again, the initial value is the Hawk, the initial Hawk, sorry, ounce populations. And this is the initial Hawk population. Right. So I'm going to start with that. Again, I want to see if I can obtain this particular graphs. So as you can see, we obtained this, right? So if we start at the number of out at 150, it remains the same throughout the number of days that I want to calculate. If I start the number of Hawks at 200, it remains the same as well. Okay, now again, we have 3 different cases here and see if we can draw any conclusions from this simulations or not. All right, so I'm going to modify the code here. The only thing that I modify is the initial values of the owls populations and of the Hawks populations. So I change this to 151 and this is to 199. I run the code one more time, so shift enter. And as you can see that the number of Hawks, right, just increase the number of owls by 1. The number of owls, if you run this model for a long time, then population, the owl population will run to infinity, which is unrealistic, right? And the number of Hawks will die down, right? Eventually, in this competitions model, the owls win at the end, right? Even though the number of owls at the beginning is less than the number of Hawk, but by increase the number of owls by 1 from the equilibrium value, right? You can see the number of owls increase to infinity. Now you modify the code one more time so that it represents the second case that the number of owls initially is 149 and the number of Hawks initially is 201. And in this case, the number of Hawks will win and will get to infinity, and the number of owls will decrease to 0. Now, in the last case, you just start with 10 owls and 10 Hawks. Let's see what happened. So the number of hawks will win, and so let me put the y limit here so that I just want to see up to so from 0 to 100 only. You see what happened. So as you can see, the number of out eventually will die out, right? So what can we say about this simulations, right? So we can say that the equilibrium points, right, is not stable, or is unstable, right? Because the system is very sensitive to the initial values, right? Because if you just change a very small number of owls or hawk, the population will change drastically. Okay, so that's the conclusion, the big conclusions that you can draw from these calculations. So the number of owls, let's say, is equal to 150, which is the equilibrium point or equilibrium values. So the owls remained at 150 forever. If the number of out in the population in the habitat is 151, then you have that the owl's populations grows without bound. And when the owl is 149, the owls will die down. Right, so you conclude that the model is extremely sensitive to the initial conditions. So you draw the conclusions that the model is extremely sensitive to the initial conditions.